Algorithm-aided design tools are quickly becoming a standard of the AEC industry. They can bring endless opportunities for customization and automation within your design software and allow more experimentation and optimization within your designs. Algorithms-aided design can be intimidating to a new user, but the most important thing you need to get started is a problem you want to solve. Then the true possibilities begin to open up. My name is Sarah Barrett, and I'm a Senior Architect Product Specialist at Vectorworks. In the following presentation, I discuss some basics of algorithmic modeling, give some examples of scripts that you can build in BIM software, and look at several real-world success stories. I hope that after watching this, you are inspired to give algorithms-aided modeling a try.
What is algorithms-aided design? Algorithms-aided design, also called algorithmic design, is the process of using an algorithm to generate a form or complete a task. An algorithm is essentially a formula, a recipe, or a series of instructions. So algorithms-aided design means using a pre-designated set of steps to drive a three-dimensional design. These two images could be considered algorithms because they are a series of instructions that, when completed, generate a predictable result. The biggest difference between these two images and the algorithms we'll be talking about today is that these instructions must be carried about by a human, while algorithms-aided design in BIM software is instructions carried out by a computer. For algorithmic design, the work comes from creating the recipe or algorithm. Creating a process is a different way of designing than most architects and other designers are used to when it comes to generating form. Most designers generate the form organically via trial and error, and once they have the form, they break it down into a recipe for construction, which are, in essence, architectural drawings. Algorithmic design essentially reverses this process, calling for the recipe in order to generate the form. To use algorithms-aided design in BIM software, you need an interface to create these algorithms, either graphical or text-based, and you need an understanding of the software's capabilities. This is because your algorithm must operate within the rules of its parent software, or in other words, use only the tools or components available in that software. These interfaces have been around for a long time. Before we had design software where we could use a mouse and draw, we had a text interface to input commands. We've also had similar interfaces in other software, such as word processing and spreadsheet software. In these software applications, the scripts that are produced are often called routines or macros. These follow the same principles as those of algorithms-aided design, creating a recipe that dictates actions taken by the software. Just like the routines and macros that you may have used in other software, algorithms-aided design tools allow you to automate processes that you can otherwise do manually in the software. The first instances of scripting interfaces in design software were text-based. These interfaces use programming languages that are more generic or standard, like Python or C++, or they use programming languages specific to the software. More recently, graphical scripting interfaces have been incorporated into design software. Graphical interfaces are becoming more and more popular. They're often easier for those without prior computer programming knowledge to comprehend. These graphical interfaces can be used to create flowcharts where each box or component or node is an action, and its connection and order within the other actions in the algorithm are what define that process. The geometry shown here was created using an algorithms-aided design tool in BIM software. So today I'm going to be demoing Marionette, the algorithmic design tool in Vectorworks, But I think it's important to note that there are similar tools in other software. Each tool does a similar thing for its parent software. It automates existing functionality. If I were to demo a different tool in a different software, any variation would be more dependent on the parent software than the algorithmic design tool. So back to this geometry. It's a series of curved tubes, their curvature dictated by 3 separate NURBS curves. The NURBS curves were modeled directly, while the tubes were generated when the algorithm or network was run. In this view, you can see the network that created the curved tubes. Because this is a graphical script, you can get a sense of how it works by reading the names of the different nodes. Each node in the algorithm represents either necessary data or actions to be performed on that data. You can see that 3 named curves are being divided in the same number of points. Those points are being collated into different lists, and those point lists are being used to create more curves. Those curves, along with a circle, are used to create the path extrudes that are the final output of the network. This type of network relies on existing geometry. In this case, 3 NURBS curves, but this isn't always the case. Some networks create geometry simply from coordinate and number values. Because the NURBS curves are the basis for the tube geometry and not generated by the script, they can be edited manually. If any of the NURBS curves are adjusted and the network is run again, the tubes will be recreated following the new location of the NURBS curves. Once a network like this is built, it's easy to change certain values and test different iterations. If I wish to change the radius of the tubes, I can change that value and update the geometry again by running the network. The old geometry will be deleted and the new geometry will be created. Now that we have an idea of what this network does, let's see how to build it. First, we start with 3 NURBS curves. You can see the name of each of these curves at the bottom of the object info palette when the curves are selected. These curves have been drawn in the software with the traditional method of clicking points with a mouse. This is how most of us use our design software. Because these curves were drawn manually and not via a script, there needs to be a connection established, a way to refer to them in the network. This can be done by giving each of the curves a unique name. To connect the named curves to the network, I need name nodes. Name nodes allow you to reference an object by typing that object's name in the name field. Once the names are in and the network is run, any wires coming out of these name nodes will allow the curves to be analyzed or manipulated. Because these curves were drawn manually, however, they can still be edited manually without losing their connection to the network. The name node was located in the input folder. All the nodes in this folder are similar in that they can be used to start a network or to add parameters to a network. There are nodes that allow you to enter text, numbers, and coordinates into networks. There is a node similar to the name node that references existing objects, but instead of looking for a specific name, it looks for types of objects. You can also filter those types with more specific criteria. The node is called Objects by Criteria, and with it you can reference, for example, all the walls in your model or all the objects in a particular class. This can be useful if you want to make changes all at once to a particular type of object. Now that my curves are in the script, I need to divide them into equal segments and get those coordinate values. I'll use a divide curve node. This node is specific to NURBS curves, so it's in the NURBS folder. As I mentioned before, algorithmic tools are dependent on their parent software, so the way the nodes are organized caters to the way the software is organized. Vectorworks has several different 3D object types, including NURBS objects, solid objects, and parametric objects. This is why there is a specific folder for NURBS nodes. Once the nodes are in the drawing area, I can connect the name nodes to them. I'll also need an int node for the number of divisions. This is located in the inputs folder, just like the name node. You can see that I can type a value into the integer field to give the node a value, and then I can connect it to the divide curve nodes as well. This is where algorithmic modeling tools are similar across softwares. They all have these nodes or components that act like script packages. These script packages can be connected together via wires. One way you can think of it is that each node is a formula. The labeled circles on the left of the node, the inputs, are variables of the formula, and the circles on the right side of the node, the outputs, are the result of that formula. You can see that the divide curve node has two variables. One is hcurve, and the other is idivs. You can also see that the divide curve node has one result, list points. These labels, along with the node name, do a lot to explain what the formula is. You can extrapolate that you are taking a NURBS curve and dividing it into a number of segments, and the output will be a list of points, each point at a division of the curve. H, I, and list are all prefixes that help you understand what type of information is passing through the node. H stands for handle, which is a term used in some scripting languages to refer to objects generated elsewhere and used within a script. In the context of Marionette, H stands for actual geometry. The I stands for integer, meaning a whole number. Integers are always whole numbers because they represent counts. This is opposed to real numbers, which represent amounts or distances and can therefore be fractional. Finally, list stands for multiple values instead of a single value. Lists are an important and powerful aspect of algorithmic design that I'll talk more about with the next nodes. Next, I'll add a locus node. This node is not necessary for the script, but it's useful for understanding what has been built so far. Locus nodes are located in the locus subfolder inside the objects folder, similar to the divide curve node. The outputs of the divide curve node are connected to the P input of the locus node. P stands for point or coordinate. The function of a locus node is to create a locus at the specific coordinate. The output of the locus node is hlocus, so that means that this node is generating geometry. When the network is run, you can see locus points along each of the curves. Connecting multiple lists of points to a single locus node creates a locus for each point value. This is an important value-added aspect of scripting, the ability to use one command to create multiple objects. This is something these nodes do automatically. They repeat their scripts or formulas on every value that passes through them. Some nodes handle lists of objects differently than others, and in Marionette, nodes with a specific list handling have their names written in gray text as opposed to black. Because the locus node, and therefore the network, has created geometry, you can see the geometry selected in the drawing area. If you look at the object info palette, you can see that what is selected is actually a group. When a network like this is run, it always creates a group of geometry for each geometry creation node. You can see that the geometry has a name. In the bottom of the object info palette, the name is Marionette Group Locus _42. This makes the name unique to the node that produced the geometry, and if the network were to be run again, the old group would be deleted and a new group of geometry would be created. This means that the geometry stays connected to the network. If I were to ungroup the geometry or change the name, its connection to the network would be severed. Connecting the geometry to the network allows you to test multiple iterations of the script without creating multiple versions of the geometry. Next, I'm going to add some data flow nodes, an ordered list node and a collate node. Data flow nodes are the most powerful types of nodes in scripting. Another term for them would be list handling nodes, which I mentioned earlier. These list handling nodes allow you to create patterns and sequences. They allow you to perform functions on multiple objects at once instead of one at a time. This is where algorithmic modeling gains efficiency over manual modeling. These nodes are more universal to algorithmic modeling tools across platforms because their code is not specific to the software, but more often is general programming functionality. The ordered list node allows you to connect multiple outputs in a particular order and create a single list. In the network, I'm taking the 3 lists of points from the divide curves and creating a single list. The collate node takes a single list and separates it into multiple lists. It works in a way that's similar to how you might collate multiple copies of a multi-page document, where that document was printed one page at a time with multiple copies of each page. The collate node has a second input that needs to be connected. This input is a number that represents the length of each of the initial lists, the number of pages in the multi-page document from the previous metaphor. There's already a value in the script which can be used for this input, the integer for the number of divisions of each curve, but it needs a little adjustment. The number of divisions of the curve is the number of segments, but the number of points that is created from those segments is actually one more. There's a specific node for adding 1 to a value, and this node is located in the math folder. I can add that node to the drawing area, connect the int node to it, and connect it to the collate node. Now the script will create a series of lists that have 1 point from each curve. Let's see what I mean by a series of lists. I'll get a print debug node from the debug folder. Debug is a term used in computer programming that means to test and check for errors. The print debug node will print whatever values pass through it. The print debug nodes I've placed are set to show the date and time that the script was run, the number of values passing through the node, and the first 10 values, as well as what type of value those 10 values are. When the script is run, text objects appear directly below the print debug nodes. You can see the values from the ordered list and the collate node. There are 63 values coming from the ordered list node and only 21 values from the collate node. If you look at the first value from the ordered list node, it is a 3D coordinate with an XYZ value. After the value, you see that the type is tuple. Tuple is a mathematical term meaning a specific list of elements, and this term is used in computer programming to describe lists of objects that are not meant to be separated, like XYZ coordinates. Tuples are written inside of parentheses, separated by commas. If you look at the first value of the collate node, you see the first value from the ordered list node as well as 2 more values. These values are inside of brackets and then separated by commas. Brackets signify lists. Lists and tuples are a little different in that lists can have values added to them, subtracted from them. They can be arranged or manipulated in lots of ways while still remaining lists. Tuples must be exploded in order to be changed. It may seem like I'm getting a little into the weeds here, but I think it's important to delve into this example in order to show how information works in scripting, even if it isn't necessary to know this to use an algorithmic design tool. The print debug nodes were not necessary for the script, so I deleted them. The next step is to create curves from the list of points. These curves will serve as the basis for the final extrudes. I'll get a curve node from the NURBS folder and connect the output of the collate node to the list points input of the curve node. Because the output of the collate node is a list of lists, this will create multiple curves. When I run the network, you can see the curves appear at the same location as the loci. The curves, however, are straight and angled, but we want them to be smooth and rounded. This can be changed by attaching nodes to the other inputs of the curve node. You may have noticed that some inputs on nodes are empty, but they still work when the network is run. This is because nodes often have default values that are used when there are no other values from the inputs, and this is the case for the curve node. The default values give us the curves that you can see. The two nodes I need for the inputs are a Boolean node and a real node. The term Boolean in coding is meant to represent an either-or value and is most often defined as true or false. The Boolean node allows you to choose between two options. In this case, it's a choice of by control points or not by control points. The default value for the Boolean node is false, so I will leave it as it is. The next node is a real node for a real number. A real number is any number representing a measurement, a distance, length, volume, etc. If you're familiar with NURBS geometry, you know that NURBS can be created using either control points or interpolated points, and the degree of a NURBS object is its degree of curvature. Interpolated NURBS curves pass directly through the points used to describe them, but control point NURBS curves do not necessarily pass through the points. And for a degree of 1, NURBS turn sharply at each point, while a degree of 3 is the typical default curvature of NURBS. With the degree changed to 3, the curves have the smooth shapes that we want. Now that I have paths for the extrudes, I need a profile. I'll use a circle node that creates a circle based off of a center coordinate and a radius. I can copy the real node already in the drawing area for the radius, and I can then change the value. The value of a real node will be read as document units, which in this case is inches. I don't need to change the P center value from its default of 0, 0 because the circle will be incorporated into the extrude along path. Now I will get a path extrude node from the solid folder, connect the circle output to the profile input, and connect the curve output to the path input. When I run the script, you can see that all the curves have been replaced by extrudes. An interesting thing is happening here. Even though I only created one circle, that circle was automatically copied and used for each of the curve paths. This is the default way that nodes work with uneven input value lists. They copy the last value of the shorter list until it matches the length of the longer list. And this also happened with the curve node. Now that the script is built, there are several values that can be easily changed to create a different iteration. There's more work up front to build the script than it would be to create this geometry manually, perhaps, but the efficiency comes in when you want to change one of the values. Changing any of the values of the purple nodes will result in a new iteration. There are several things I could do with this network now that I have it. I can wrap it by converting the node to a single wrapper node. This makes it easier for running and storing the network. I could convert it to a plugin object so that if I change a value, it updates dynamically. I could convert it to a menu command if I wish. That functionality is all specific to Marionette. Algorithmic design tools have different functionalities in other software, but what I've demoed here is pretty universal to most other softwares. This renovation project of an existing Greyhound bus station, and it contains two objects created using algorithm-aided design. The first is a railing that is pretty similar to the script that I just demoed. It uses curves to generate the shape of the overall railing as well as the thickness of the posts. This geometry has been placed inside a symbol, and the views on this symbol have been generated and placed on a sheet. This means that the object can be dimensioned and annotated. If the size or shape of the object is changed in the model, these views will update as well. Within a symbol, it's also possible to generate 2D representations for each view of the object and save those as different levels of detail. This means that the object and all its different 2D representations can be saved as a resource and used in multiple files and projects. The other algorithm Zeta design object in this file is this floor tile array. This is what we call a marionette object. It's a script that has been converted to a plugin object. If I right-click on it and choose Edit Script, you can see the marionette network that created it. When it is selected, you can see parameters in the Object Info palette. I can edit fields in the Object Info palette and it'll update automatically. I don't have to rerun it. With this object, I can choose a predetermined pattern or a random pattern. And the BIM aspect of this object is that the tiles that make up the array are symbols that have data attached to them. They have material data as well as manufacturer and cost data, and I can pull that data into a worksheet or schedule. This schedule is reporting on the tile symbols in the file, and when the script is changed and the number of each tile type changes, I can simply recalculate the schedule to see the updated cost. My last example is a script that performs analysis on its own geometry. NURBS curves and surfaces can be exciting to use when creating organic forms, but they're not often practical for fabrication because structures are mostly made with rigid material. When NURBS surfaces are used in building design, they often have to be converted to panelized structures, and those panels need to be analyzed and fabricated. So this script does just that. The way this script works is it takes 3 existing NURBS curves, similar to the first example we looked at, and it creates a lofted NURBS surface from them. The script then takes that NURBS surface and analyzes it, converting it into a grid. After the script creates the panels based on the UV values of the surface, it applies a color to the panels based on the extent to which it is out of plane or warped. The colors are set to show pink as the most warped and green as the least. The script not only colorizes the panels, but also arrays them in a cut sheet. The color is useful for a visual understanding of the design, but numerical data is important too. The script also creates a worksheet that lists the panels by ID number, distance out of plane, i.e. the distance that the 4th vertex of the panel is out of plane from the other 3, and the total area of each panel. This is a little different than the last example I showed of the floor tile array. That script did not generate its own worksheet, but it had data that I could easily extract. So this script has the schedule built in. Either method of reporting works, but it depends on how you wish to use that data. For the floor tile array, I wish to use that data to generate quantity takeoffs, so it made sense to have it as part of my documentation. But with this panelization script, I would want to use that data to inform my design. So I can use that information either to adjust the overall shape of the surface, or I can change the number of UV divisions in the script to change the number or direction of panels. These decisions can be more easily optimized because different iterations and scenarios can be created efficiently with algorithmic design. Once the design has been finalized, the data extracted by the script can then be used for fabrication purposes. Now that we've talked about some basics of algorithm Zeta design as well as some more complex creations, I want to share case studies of algorithm Zeta design in practice. The first case study is a success story of a designer who used algorithmic design to scale up his business. Norbert Rostaki is a photographer, filmmaker, sculptor, and designer. Originally from Krakow, he currently lives with his family near Basel, Switzerland. In 2015, he founded Move Art GmbH for the professional manufacturing and marketing of his multifunctional play sculptures for public spaces. He's won multiple awards for his play sculptures, including the German Design Award and the European Product Design Award. Here is an example of one of his clay sculptures in Arosa, Switzerland. Arosa is a picturesque small town in the Swiss Alps, and Rostaki was commissioned to create furniture for the public park. The furniture should be inviting and accessible to all ages, as well as unique to the park. This piece is the largest in the park, and it's specifically designed for this location. The design comes from the name of the town written in script. That name was converted to a NURBS curve, and that curve defines one edge of the sculpture, while a straight NURBS curve defines the opposite edge. Here you can see another view of the Arosa script sculpture, as well as other pieces that function as benches. Each piece is made of multiple pieces of wood that arc and curve to form a surface. This is a playground sculpture designed for a school, and it's one of his climb slide models for which he won the European Product Design Award. Before Rostaki discovered marionette, he was modeling each sculpture individually. This would take a good deal of time, as he had to do a lot of manual calculations to figure out the length of each spoke, as well as where holes would need to be drilled in each piece to join one to the next. He had to build scale models, and there was a lot of back and forth with the factory that fabricated his sculptures. With marionette, he was able to greatly reduce his design time, as well as the time spent generating shop drawings. He created a script that is based off of NURBS curves in a similar way to the script that I demoed earlier. This script generates each individual piece based off of those NURBS curves. If the NURBS curves are changed, he can simply update the script to see the new result. Here, you can see the marionette object that is the same model as the climb slide we saw in the last slide. Because it's a marionette object, it can be saved as a resource in his own content library. He can edit the NURBS curves that are the basis of the design by right-clicking and choosing Edit Control Geometry. He can also change parameters in the Object Info palette. This script can generate a very accurate model of the object, with each piece having the correct curvature. The object can then be exploded, and each piece can be documented with shop drawings simply by creating views and annotating them. Because this model is highly detailed with a lot of curvature, it can take a while to generate the form from the script. Built into the script is the ability to lower the detail level for the purpose of design iteration and exploration. At low detail, he can quickly change the shape of the NURBS curves and then rerun the script to see the result. The marionette object also generates its own schedule every time something is changed. This schedule labels each piece and lists its dimensions, and his manufacturer can use this schedule to fabricate the pieces. This form of scheduling is similar to the panelization example I showed, but the schedule can also be placed on a sheet and used in documentation. Using marionette to generate the model and the necessary calculations allows Rostaki to focus on the design itself. He has more time to really hone the design and to better cater to the client's needs. To better inform each design, he came up with what he calls a human ignition profile, where he works with the client to decide to what extent the sculpture will provide each of 8 different functions. The functions are protect, sit, rest, balance, climb, slide, hide, and swing. The different functions can be prioritized based on the expected users of the sculpture. If the users are expected to be children, then the climb and slide functions might be prioritized. If the users are expected to be elderly, the sit and rest functions might be prioritized. This level of granularity in his designs is possible because the modeling and the documentation have been so greatly streamlined. Algorithm-Zeta design has also allowed him to greatly scale up his business. He went from being able to only work on one design at a time and having that design take several months, to being able to design and fabricate a new sculpture in only a few weeks. He now has a whole catalog of existing designs that can be ordered directly from his company, and he can also take on more unique commissions each year. Unique commissions like this dragon design. Norbert Rostaki ascribes the success of his business, Move Art Swiss, to Marionette. Principal Architecture is a firm that also maximizes efficiency using algorithmic design. Principal Architecture is a 6-person firm based in Vancouver, British Columbia, and works primarily with public institutions, municipalities, and community groups on projects that enhance public spaces. The firm strives to embrace the city's culture of wood through design. By exposing the tension between the idyllic forest in its raw form and the resulting lumber used to urbanize the city, the firm finds new ways to celebrate this important foundation of Vancouver's history. Principal Architecture was tasked with designing an exhibition exploring the history of wood in Vancouver. The project had a daunting challenge. The team only had 5 weeks to completely design and build it. The exhibition content itself had also not been finalized, so there was not even a set of known exhibition materials to work with. Searching for a way to create an immersive emotional experience within such a short turnaround time, the firm decided to use Marionette. With algorithmic design, Principal Architecture was able to maximize construction and documentation efficiency while still taking the time they needed to hone the design. Because the exhibition materials were a big unknown, it was important that the exhibit itself be a thought-provoking commentary on the history and use of wood as a construction resource. Drawing on the disparate phenomena of the experiential aspects of the forest and the use of the tree as a construction resource, the design used wood to create an environment that was both romantic and rational. A series of exhibit spaces in the shape of large tree trunks. The interior of each exhibit space consisted of a traditional post and beam structure, a popular building method in Vancouver. When building the digital model, the firm first used NURB surfaces to create the exterior shapes of the tree structures, and by using digital walkthroughs and visualizations, they were able to convey the design as well as the experience of traveling through the space to the client. Modeling the tree structures within a digital model of the existing exhibition space, the firm was also able to incorporate and work around obstacles such as ductwork and structural beams, as well as carefully plan out egress and code specifications. To create a digital model and construction documents of this design within such a shortened time frame, the firm had to bring together 2 disparate design methods: organic sculpting and data-driven generative design. This was in keeping with the overall design motif, combining the romanticism of the forest with the logic of wood construction. To understand exactly what the parameters would be for the interior structure, the firm first built a physical prototype of one of the tree structures. This helped them come up with a logic that they could use within the script. Marionette would be used to script the post and beam structure within the NURB's tree trunk shape. Here you can see the input parameters of the script on the left, the original NURB surface in plan view in the center, and on the right, the skin, sleepers, rings, posts, and beams generated by the script from the surface. The script was then copied for each tree structure, and the necessary parameters were changed for each copy of the script to match what was needed based on the size and location of each structure within the space. That way, when new information was received about the exhibition space itself or the content of the exhibition, the surface of the structures could be reshaped and then the scripts rerun to update the interior structure. Because the algorithmic modeling tool was being used within BIM software, the firm could not only generate the geometry from the script, but also visualize and document it by extracting construction drawings directly from the generated geometry. Fabrication outputs and shop drawings could also be created directly from the model. Being able to adapt to new information so quickly was essential to the success of the project. For example, the height and location of the ductwork in the drawings of the exhibition space that were provided to the firm were found to be incorrect well into the timeline of the project. Without BIM modeling to visualize all the aspects of the space and algorithmic modeling to efficiently update the structure, the necessary changes that had to be made to the design would have set the project back significantly and made the timeline impossible. Principal Architecture had made the switch from 2D drafting to BIM shortly before this project, so they were aware of the efficiency gained from extracting drawings from the model, but the ability to automatically generate the model itself was another huge boost in efficiency. The firm likened Marionette to a robot friend that does the work you dread. Since they knew they wouldn't have the time or resources to continually redraw and integrate changes manually, they relied on the algorithm to do the heavy lifting. Because the form, assembly, and fabrication files of the digital model were controlled by the script, the firm was able to respond to the evolving requirements of the project and immediately be able to represent the changes to the client, as well as feel confident that the project could be built in the time given and up to code. My final case study is a custom residential project by Alchemy Architects. Alchemy Architects is a firm based in Minnesota and has been internationally recognized for their We House concept, a modular-friendly design system that emphasizes space efficiency, sustainability, and quality over quantity. Alchemy Architects design structures to be highly efficient as well as sensitive to the site and the natural environment. They prefer to use local materials not only to enrich the design, but also to keep the carbon footprint of their design to a minimum. The particular project I'm going to talk about today is not a wee house, but it's still quite small. Located on Squam Lake in New Hampshire, the project must keep the floor area and volume of an existing dilapidated cabin on the site. Eric Winter, an architect at Alchemy, describes the design as metaphorically a box of trees. The diagrams here tell the story of the design. The parametric trees bring light into the interior and define the spaces. Because the trees were irregular shapes, Marionette was used to create the supporting structure of the tree shapes, much like the project by Principal Architecture. This structure was then modified to fit into the structure of the building and inserted into the overall model. Alchemy was an early adopter of BIM and has been using a full 3D workflow for some time, but this project has been more modeling intensive than most. Very few aspects of the design use typical building elements, so much of the model was created using custom 3D geometry. Even though they didn't use regular BIM tools to create their model, they were still able to add data to their custom geometry, allowing them to continue to take advantage of a BIM workflow. The inspiration for the design was the landscape and history of the area. Squam Lake is surrounded by trees, and the local industries are mainly lumber and canoe building. For reference, Squam Lake was where On Golden Pond was filmed. White oak is used for both the interior and exterior of the building, as well as for the boathouse. Where the main house is a box full of trees, the boathouse is a fallen tree. This is something you can find all over the bottom of Squam Lake, fallen trees near the shore. This was also modeled using custom 3D elements and algorithmic design tools. Even though the Squam Lake residence isn't technically a wee house, that system greatly influenced the design. Alchemy sought to maximize sustainability, design efficiency, and durability with affordability, all while achieving crafted, significant architecture. Marionette and Vectorworks were vital to the process. Algorithmic design tools may seem intimidating and obscure to designers that have never used them, but I think that these examples show how they can be used to maximize efficiency, even with work that may not be thought of as the typical parametric design style. This image here is perhaps a little frivolous for the subject of algorithms-aided design in BIM software, but I think it shows just how far you can go with a tool like this. The script that created the object on the left takes an image, the image on the right, analyzes its colors, creates a random pattern, and applies the averages of those colors to each segment of the pattern. It's definitely the most fun I've had using Marionette, so I wanted to share it here today.